All right, for this first problem here, we're looking at the motion of this planet around a star here. This made-up planet around a new star, and what we have are the arguments of two students who are talking about where the velocity is greater, here at A or over here at B. And this is something that you'll see fairly frequently actually with the AP exam. Sometimes they will give you these argument ones, and you have to evaluate the quality of the argument. So let's go through each argument and talk about what parts are correct and what parts are incorrect. And we don't necessarily need to say in this first part A which student overall is correct, but we do want to comment on which aspects of the reasoning are correct or incorrect. All right, so let's start with student one. The force of gravity depends on the masses of the two bodies. That part is correct. That's one of the things that affects the force of gravity, which remains constant, so gravity should remain constant. Here's the issue, is the other thing that gravity depends on, if we think about it, Fg equals g m1 m2 over r squared, is this r squared value. So that part is going to be incorrect. Gravity is the only force acting on the object, and it does provide a centripetal force to keep this turning. However, we're not moving in a circular path, so that part's going to be incorrect, and that ultimately leads to the overall answer being incorrect. But again, we're really just commenting on the correct and incorrect parts. So for my answer for part one, I'm going to say the student's correct that gravity depends on the masses of the object, which is shown by the universal law of gravitation, and also they're correct that gravity is the only force and is that inward force making the object turn. For the second part here, I'm going to say the student's incorrect, student one that is, because the force of gravity also depends on the distance, and also it's going to be an elliptical orbit, which is what Kepler's first law tells us, not necessarily circular though. Let's go ahead and move on then to the second student and highlight the correct and incorrect things. So the second student does point out that the orbit is elliptical. And so they do an energy argument here, and there's a lot of things that are correct about that energy argument. The first is that the gravitational potential energy is smaller in B than in A. Okay, so as we move closer, we are losing gravitational potential energy, and that means then that the kinetic energy and therefore the speed will be greater at B because energy is conserved in this situation. The one part that is incorrect here is this line about no forces acting within the system. Okay, there is obviously the force of gravity, it's just that gravity is a conservative force, so it doesn't affect the energy. For part 3 of A here, I just said the student's correct. With the energy argument, gravitational potential energy is being converted to kinetic to conserve the total energy of the system, so it's traveling faster at point B. And then for the incorrect part, it's just that one line about there being no forces in the system. There are forces, it's just that it's conservative forces, and so it doesn't affect the total energy of the system. It still remains constant. For this next part, we want to relate the force acting on the planet at 2 points, at point A and point B, knowing that at point A, the star is 3 times the distance than it is at point B. So we're going to think about Newton's universal law of gravitation. G m1 m2 over r squared in this case is going to be the mass of the planet and the mass of the star. I'll call that little m and big M. And then over the distance, and for A, I'm going to say that distance is 3r, that quantity squared. For B, same thing on top, all right, because the masses are the same, but now it's just going to be over r squared. So we can say that FA is 1/9, because we're going to have to square that 3, okay, we have to square everything in that expression, times GMM over r squared, which happens to be the same as that force for B. So I can say the force for A is 1/9 the force for B, or you could have said the force for B is 9 times the force for A. Either one would be an acceptable way of relating those two. For part C here, we want to draw the direction of the velocity on the planet at point A and also the direction of the force. So the force is going to be going inward, bringing the planet towards the star, so it's going to look something like that. And the velocity is going to be tangent to the ellipse at this point, so something like that. For the last part, we want to know if the speed of the planet changes as we move from B to A, and there's a few ways of explaining this. I think the easiest one, and the one I'm going to use, is energy. Usually, if you can explain something using energy, that's the easiest way of explaining, solving, whatever. You really want to be thinking about using energy if you can. So from an energy perspective, our argument will go something like this. Basically what student B had, or student 2 had said, as we go from A to B, gravitational potential energy becomes kinetic because the objects are getting closer to each other, decreasing the gravitational potential energy, which means the kinetic energy is increasing and therefore the speed is changing. The other argument you can make would be, you can see here that there's a component of this force of gravity in the direction of the velocity. That's going to lead to the object speeding up because we're going to have an acceleration also in that direction. So that's one way you could explain it. You also could explain it with angular momentum. That one's a little bit trickier, but we can say that the angular momentum of the system is 0 because there's no outside torques. And look at our one equation for angular momentum, which is the L equals RP sine of theta. So as the radius between the planet and the star gets smaller, all right, in order to conserve angular momentum, the linear momentum and therefore the velocity must get greater. Any of those arguments are valid, but I'm going to use the energy one because I think that's the simplest. All right, for this one, we have a situation where there's a box sliding down a ramp here, like so. It then enters this circular, semicircular track and goes around in half of a circle. We see the top view over here. And so the first thing we want to do is we want to figure out the velocity at this point right here when it gets to the bottom of the ramp. Now, we haven't done the energy unit yet, but you could solve this either with energy or with forces and kinematics. As I've said many times, energy is usually the easiest way of solving it. So even though we haven't done that yet, I'm going to go ahead and solve this with, or haven't reviewed it yet, I'm going to go ahead and solve this with energy. So we're going to start with gravitational potential energy at the top of the ramp here. By the time we get to the bottom, all of that has become kinetic. And because it's a frictionless ramp, at least the ramp itself is frictionless, we're not going to have any work that is done. Okay, so it's going to be mgh equals 1/2 mv squared. The m's, of course, divide out. And so we really just need to figure out what this height is here in order to be able to solve for it. So thinking about that height, all right, we know that the length of the ramp here is x. The angle of incline is theta, so that means this height right here is going to be x sine of theta. All right, and so I can say g times x sine of theta equals 1/2 v squared. So that means that my velocity, when I solve for that, is going to be the square root of 2gx sine of theta. All right, moving on to B, we're going to be looking for an expression for the normal force that the wall exerts on the box when it first enters the curve. And so we're going to be thinking about the fact that this box is traveling in a circle, so I'm going to be thinking about all of my circular motion concepts. So I know that when it first enters, there's going to be an inward force keeping it moving in a circle. In this case, and this is the overhead view, I just took it from here. In this case, that inward force is going to be the normal force, and that's what we're solving for. So I'm going to go ahead and set this up, saying sum of the forces is equal to m times a. The normal force is the only force keeping it moving in a circle, providing that centripetal force. This is the normal force from the wall, by the way, not the normal force from the table. Okay, that's going to be equal to the mass of the box times its acceleration, which for a circle is v squared over r. So our normal force is going to be equal to m times v squared, and there's our v. All right, so I'm just going to remove the square root, so it's going to be 2gx sine of theta divided by our radius, which we're told is x over 4. We can go ahead and simplify this. The x's divide out, and that 4 gets moved to the top here, and so what we're left with is our normal force is going to be equal to 8 mg sine of theta. So moving on to part C here, we want to consider what happens to the rate at which the box slows down as it's traveling around the curve. And so let's just think for a second about the forces acting on it. Slowing down is really an acceleration thing. And so we want to think about what forces are causing that acceleration. So once again, I'm going to be using this top view here. There is, of course, gravity going straight down into the screen, and the normal force from the table itself supporting that box, but neither one of those is going to cause the box to speed up or slow down because those forces are balanced. So the forces I really care about in this case are the normal force from the wall, all right, which is providing that inward force, and the frictional force. So we do have a frictional force only between the box and the wall, but that will affect the motion of the box. And so that frictional force is going to be going backwards, opposite the direction that the box is moving as it slides along this curved wall. So what I would think about is this. The normal force ultimately is going to affect the force of friction. We know that the force of friction is going to depend on mu times the normal force. So mu is going to be a constant. That's not going to change. That just depends on the materials of the box, the materials of the wall. The normal force, however, that can change. And the reason why that's going to change is, as we saw in this last problem, that normal force is equal to mv squared over r. All right? And so that means that as the box goes around, friction is going to slow it down, decreasing the velocity of the box. That in turn is going to decrease the normal force, which will decrease the force of friction. Okay, so as it goes around, that frictional force that's slowing it down is actually going to ultimately reduce that frictional force, which means that the rate at which it slows down, the acceleration of it slowing down, will be getting smaller as it travels around the curve. So in terms of writing this argument, the first thing I would say is just start with a pretty clear fact that friction is the force that slows the box down as it travels around the curve. The next thing that I would say is really just citing this equation here and saying that the force of friction depends on the normal force between the box and the wall, okay? That's really deriving from really what friction depends on, that equation. And then I think the next point you make is the normal force from the wall provides that centripetal inward force. As the velocity decreases, the normal force also decreases, and you can cite this equation for evidence of that. All right? And so we've laid out three important facts here. Friction slows the object down. Friction depends on the normal force, and the normal force, as the velocity decreases, is also going to decrease. So now all we need to do is tie them all together and say that as the velocity decreases, the normal force and therefore friction will also decrease. That means that the acceleration of the box while it's slowing down will decrease as it travels around the curve. All right? So we've laid out a few important facts that we can either say from explaining the situation or looking at the equations and how different variables depend on others, and then we bring them all back together to answer this question of how does the acceleration, the rate at which it slows down, change as it goes around the curve.